Hello students, welcome to MEMONEET. This is Ravikant, your physics teacher, and today we are going to discuss the chapter the thermal property properties of matter, which is your syllabus for BPT 10, right? And hope you all are practicing the questions and utilizing your time well to study things, right? So let's start with thermal properties of matter. Thermal means related to heat. So heat is a type of energy which could be sensed in terms of hotness and coldness of the body, right? A body, if it is hot, it means it has taken some heat energy, and if it is cold, it means it has lost some heat energy, right? So heat is something which has been reflected by a body in the form of temperature. Now, what is heat? The heat is type of energy, and heat is the cause. What is the consequences of heat? Consequences of heat is in the terms of temperature, right? That is, if we supply heat to a body, if we supply heat energy to a body, its temperature will increase, right? Its temperature will increase. And if we withdraw heat energy from a body, its temperature will decrease. So because of the supply or withdrawal of the heat, the temperature of the body is changing, right? So the heat is the cause and the temperature is the effect of this heat energy. Heat energy, right? So the unit of heat is given is because it's an energy. So energy, it's one of the unit is joule, and another unit which has been commonly used is calorie. So one calorie is equals to 4 point joule, right? 1 calorie is 4.2 joule. Now what, how calorie is been defined? Calorie is been defined as it is the amount of the heat required to raise the temperature of 1 gram of water, to raise the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade, right? That is the differences of 1 degree centigrade, right? So the amount of the heat required to change the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade. Why this range, that's 14.5 degrees centigrade to 15.5 degrees centigrade, this range is selected because this is a range in which the expansion of the water is even. That is, it undergoes even expansion, or its expansion, right? So I repeat the definition of 1 calorie. 1 calorie is the amount of the heat required to change the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade. So calorie is the unit which is most commonly used for heat energy, right? Whereas heat is the energy, therefore its SI unit is joule, right? Its SI unit is joule. Now temperature is the effect of the heat, and the SI unit of temperature is your Kelvin, right? Kelvin. There are other units. Temperature is also given in the form of in the terms of degree centigrade and degree Fahrenheit, right? So to discuss about degree centigrade and different Fahrenheit, we will study a topic. We are going to discuss a topic which is known as thermometry. In thermometry, we'll see that how a temperature of a body is being measured using a thermometer, right? Measured using a thermometer. So in thermometry, we will see that how that scale is being calibrated on a thermometer. Now, suppose this is a thermometer and it has the mercury bulb over here. So now this bulb is placed in a container which has its melting, which is filled with melting ice in it, right? Which has melting ice in it. Now ice is melting. So at that temperature, the temperature at which the ice is melting, this mercury in the thermometer will contract and will reach to a level. We will mark that level, and that will be known as lower fixed point, right? That will be known as lower fixed point. Now the same thermometer will be placed in a container which has a thermometer, the same thermometer in it, and the container has a boiling water, right? Boiling water. Now, because of the boiling water, what will happen? The mercury inside the thermometer will expand and will reach to a level, and this level will be known as upper fixed point, right? Will be known as upper fixed point. Now, this the distance between the upper fixed point and the lower fixed point is divided into equal number of divisions, and those divisions will be marked in the three scales or the two scales which we are going to see is that the degree centigrade scales or in the Fahrenheit scale, right? So this is the process how the calibration has been done. If it is being calibrated in degree centigrades, the lower fixed point, lower fixed for degree centigrade, let's say for your degree centigrades, the lower fixed point will be equals to taken as 0 degrees, and the upper fixed point will be taken as your 100 degrees. On the other hand, for degrees Fahrenheit, the lower fixed point will be equals to your 32 degrees, and the upper fixed point will be equals to your 212 degrees, right? So here the number of divisions will be equals to 100 divisions. So we will be making 100 divisions in the length of between the upper fixed point and the lower fixed point. And for degree Fahrenheit, we will be making 180 divisions. Divisions here will be 180 divisions, right? So from this, we can see how there are two different scales of the temperature are made. So one is the Fahrenheit scale in which the lower fixed point is 0 degrees, centigrade scale in which the lower fixed point is 0 degrees and the upper fixed point is 100 degrees. In the Fahrenheit scale, the lower fixed point is 32 degrees and the upper fixed point is 212 degrees. What I mean to say here is that if we measure the melting point of ice using degree centigrade scale, it will be measured at 0 degree, whereas if we measure it using the Fahrenheit scale, it will be measured as 32 degrees Fahrenheit. On the other end, the water will boil at 100 degrees centigrade, and in Fahrenheit scale, it will be boiling at 212 degrees centigrade, right? This is what this lower fixed point and upper fixed point means, as I told you in the beginning, right? Now, suppose the temperature has been given to you in degrees centigrade and you want to convert it into degree Fahrenheit. Then the relation between these two is C. Not only from degree centigrade to Fahrenheit into any other scale of which you know the lower fixed point and you know the upper fixed point. So the general formula for this is the temperature in that particular scale, let's say that it be T, minus lower fixed point upon number of divisions, that is upper fixed point minus lower fixed point, right, is equals to temperature in the other scale minus its lower fixed point upon the number of divisions in it, that is your upper fixed point in that scale minus lower fixed point in that particular scale. Now suppose we need to convert from degree centigrades to Fahrenheit. So the conversion formula will be, right, uh, temperature in degree centigrades minus lower fixed point is 0 upon upper fixed point is 100 minus 0, that is lower fixed point. This is equals to temperature in Fahrenheit scale minus lower fixed point is 32 upon upper fixed point 212 minus lower fixed point, that is 32. So what we get here is C minus 0, or you can simply write C upon 180 is equals to F minus 32 upon 180. Now suppose in the question they say that convert a temperature in a scale which has its lower fixed point as, let's say, 25 degrees centigrade and upper fixed point as let's say 200 degree centigrade, right? no, 200 degree, and let the name of the scale be x. So let be x. So we need to convert a temperature which is in degree centigrades to a temperature which is in x. So the formula for that conversion will be C upon 180, that is temperature in degree centigrades minus its lower fixed point upon number of divisions, is equals to temperature in x minus its lower fixed point, which is equals to 25, upon upper fixed point, that is 200, minus lower fixed point, that is 25. So the conversion formula will be equals to C upon 180, which is equals to x minus 25 upon 175, right? 175. Using this formula or this expression, we can easily convert the temperature given in degrees centigrades to a scale which is in x, right? A new scale which we had found. So this is how we can convert the temperature from one scale to another. So why we are talking about temperature? Because we were talking about heat. So if we compare between heat and temperature, see, heat is a form of energy, and this energy is being reflected in terms of temperature. It can be seen in terms of temperature, right? So heat is the effect and temperature is the cause. Now this heat which is being supplied to a body will reflect the temperature in and to what extent it will reflect depends on some factor which we will be discussing further. Before discussing further, we will have to see one more scale which is important to understand the things, that is your Kelvin scale, right? That is a Kelvin scale, the which is the SI unit of temperature. So Kelvin, for Kelvin, we simply add 273 to the temperature which is given in degree centigrades, right? Suppose we have temperature 1 degree centigrade. To convert it into Kelvin, what we'll do with plus 273. So 1 degree centigrade is equals to 274 Kelvin, right? This is the conversion in Kelvin scale. This is the way we convert it in the Kelvin scale, right? So we convert this in the Kelvin scale. So heat is the cause and temperature is the effect of heat. If we supply heat to a body, its temperature will rise. If we withdraw heat from a body, its temperature will fall, right? So one of the consequences of heat is temperature, and the another consequence of heat is the thermal expansion, that is the expansion or contraction. That is, if we supply heat to a body, the body will expand, and that is known as thermal expansion, right? Thermal expansion. So there can be three different types of shapes. First, in which length is dominant, that is one dimensional, right? Second, it is where area is dominant, that is two dimensional body. And the third is a body where volume will be considered, that is three dimensional body. Here we have only length, here we will have length and breadth, here we will have length, breadth and height, right? So if heat is being supplied to any of the shape of the body, what will happen when the body gains heat? It will expand, right? Why it expands? That is, when the heat is being supplied to the body, the particles present inside the body gains energy and they start moving with a higher kinetic energy, and because of the higher kinetic energy, they start colliding more with the nearby particles, and because of this, the energy is being transferred to the nearby particles, and the particles, all the other particles also start vibrating very fast, and because this results in, and this is followed from one particle to another, and because of this, what happens, this results in the expansion of the body, right? So suppose a body was of length L, right, was of length L naught, let's say L naught, and when we supplied heat to it, it expanded to a new length of L, right, new length of L. What was the temperature when we are supplying heat? What will happen? There will be a change in temperature. Let the temperature will be delta T, right? delta t. So the new length capital L of the body is being given by the formula L is equals to L naught into 1 plus alpha delta t. Now what is alpha over here? Alpha over here is known as coefficient of thermal expansion. Alpha is coefficient of linear thermal expansion, right? Similarly, if we have a two-dimensional body and its area is A naught, and after supplying heat it changes to capital A by changing its temperature by delta T, then the new area is given by A naught into 1 plus beta delta T, where again beta is the coefficient of superficial expansion. Okay, alpha is the coefficient of superficial expansion. Now coming to your V naught, that is for a three-dimensional body. Then if V naught is the initial volume and after supplying heat the new volume is V, then this V is equals to V naught into 1 plus gamma delta T, where gamma is the coefficient of volumetric expansion. Coefficient of volumetric expansion, right? Volumetric expansion. Now what is the relation between this alpha, beta and gamma? Alpha, sorry, alpha, beta, gamma. Alpha is for one dimension, that is linear thermal expansion. Beta is for two dimension, that is your superficial expansion. Gamma is for three dimensional expansion, that is your volumetric expansion. So if I place equals to in between, what I will do have to do is 1 upon 2 upon 3. This is what is the relation between alpha, beta and gamma, right? Relation between alpha, beta and gamma. And from here we can say that beta is equals to 2 times of alpha and gamma is equals to 3 times of alpha. This is again an important relationship which you should remember to solve the numericals, right? So what we have seen till now is that heat is a form of energy, and because of this heat, if the body shows some temperature, so heat is the cause and temperature is the effect. If we supply heat to a body, what will happen? The temperature will increase. If we withdraw heat from the body, the temperature will decrease. Heat is measured in joules, and mostly the heat is being written in calorie. What is 1 calorie? Calorie is the amount of 1 calorie is the amount of the heat required to raise the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degree centigrade, right? Now coming to temperature, temperature can be measured in three scales, three known scales, that is in degree centigrade scale and degree Fahrenheit scale and Kelvin scale, right? In degree centigrade scale, the lower fixed point, which is the melting point of ice, is taken as 0 degree centigrade, whereas the boiling point, that is the upper fixed point, is taken as 100 degree centigrade. On the other hand, in the Fahrenheit scale, the lower fixed point is taken as 32 degrees and 32 degrees, and the upper fixed point, that is the boiling point of the water, is taken as 212. Right now, I told you the conversion formula. Conversion formula is your the temperature in a scale minus lower fixed point upon upper fixed point minus lower fixed point is equals to the same thing for the another scale. Right. In Kelvin scale, if we simply add 273 degree to the temperature which is in degree centigrade, we will get the temperature in Kelvin. Simply adding 273, we will get our answer in Kelvin, or the scale will be converted from degree centigrade to Kelvin, right? Now, one of the consequence of a supply of heat is that if we supply heat to the body, we have already seen the temperature rises. Along with the rise in temperature, what will happen? The body will expand. So if we consider three types of body, that is one dimensional body, two dimensional body, and three dimensional body. So for one-dimensional body, the type of expansion is known as linear expansion. For two-dimensional body, the expansion is known as superficial expansion, and for the three-dimensional body, it is known as volumetric expansion. You have cubical expansion, cubical expansion, right? So in case of one-dimensional body, what will happen if we supply the heat? The length of the body will change, and if the length of the body will change, if we take L naught as the initial length of the body and L as the final length of the body, so the final length of the body is equals to initial length, that is L naught into 1 plus alpha delta T, and this alpha is known as the coefficient of thermal expansion, right? And coefficient of thermal expansion, the SI unit of any of the coefficient of thermal expansion is degree centigrade inverse. Degree centigrade inverse. This is the SI unit of coefficient of thermal expansion, whether it is linear thermal expansion or superficial thermal expansion or cubical thermal expansion, right? So alpha is the coefficient of linear expansion. Coming to two-dimensional body, if A naught is the initial area of the body and A is the final area of the body, then A will be equals to A naught into 1 plus beta delta T, where beta is the coefficient of superficial expansion. Similarly, if we have V naught as the initial volume of the body and V is the initial final volume of the body, then V is equals to V naught into 1 plus gamma delta T. In all the three cases, delta T is the change in temperature which has occurred. Suppose we heat a body from so in such a way that its temperature changes from 25 degree centigrades to, let's say, 35 degrees centigrades, then the change in temperature delta T will be taken as 10 degree centigrades, right? So this is what delta T will be placed in this formula here in the formula, right? So there are three types of expansion: linear expansion, superficial expansion, and cubical expansion. And the coefficient for linear expansion is alpha, for superficial expansion is beta, and for a cubical expansion it is gamma. Relation between alpha, beta, and gamma is alpha is equals to beta by 2 is equals to gamma by 3, and from here we can say that beta is equals to 2 times of alpha and gamma is equals to 3 times of alpha, right? This is what we have studied till now. So heat is a form of energy and temperature is its consequence. We have seen the scale and then we have seen the expansions. Now the next thing which we are supposed to study is your relation is also done. Yes, expansions in liquid. Now suppose we are having a expansion liquid. Suppose if we have to heat a liquid, definitely we'll have to put it in a container, and container will be made up of something. So what will happen when we suppose the liquid is filled to up this level, and when we are supplying heat to the liquid, what will happen? Heat will be supplied to the container as well as to the liquid. Now suppose only liquid expands and the container does not expand, and when the liquid expands, it reaches to, let's say, because of expansion it reaches to this level, right? Now it expanded and reached to this level, but actually the container is also expanding, and because the container expanded, what will happen? The resultant height of the container because of the expansion will appear to this point, right? So the actual expansion is this much, but it will appear only this much. Are you getting my point? So see, the expansion which is appearing to us, let's write it as EA. This will be equals to your real expansion minus expansion of the vessel, right? So I'm writing it as expansion. So this expansion will be given in terms of coefficient of expansion. So apparent coefficient of expansion, why we are taking gamma? Because liquid will be in the three dimensional, it will be considering the volume of the liquid. So gamma, which is apparent to us, that is gamma A, will be equals to gamma R, that is real expansion of the liquid, minus gamma V, that is the coefficient of expansion of the vessel. So the apparent coefficient of the liquid, apparent coefficient of expansion of the liquid is equals to real expansion, coefficient of expansion of the liquid, minus real coefficient of expansion of the vessel. This will give you the apparent coefficient of expansion of the liquid, right? So V apparent is equals to gamma apparent is equals to gamma real minus gamma of the vessel, right? This will give you the apparent what? Apparent coefficient of cubical expansion of the liquid, or you can say in this manner also, that is uh, coefficient of expansion, real coefficient of expansion of the liquid is equals to apparent expansion of the liquid plus expansion of the vessel. This formula also you can remember. Now the next thing which we are going to study is the anomalous expansion of water. Anomalous expansion of water. See what happens generally whenever heat is being supplied to a substance, whether it is in solid state or in a liquid state or in a gaseous state, it has a tendency of expanding, right? And when the heat is being withdrawn from any substance, it has a tendency of contracting. Why? Because according to the kinetic theory of gases, kinetic theory of matter, what happens? When the heat is being supplied, the kinetic energy increases, and because with the vibration increases, collision increases, and this collision is being transferred from one particle to another, and this results in expansion. On the other hand, when the heat is being drawn from the liquid, what will happen? When the heat is being drawn from the liquid or from the substance, what will happen? The kinetic energy will reduce, the vibration will also reduce, and hence the space between the particles will also reduce, and the body will contract, or the substance will contract. But in water, what happens if we start withdrawing heat from water, and as soon as the temperature falls below 4 degrees centigrade, that is after 4 degrees centigrade, water instead of contracting, it starts expanding, right? It starts expanding. So when we cool water below 4 degrees centigrade, what happens? It starts expanding, and this expansion is known as anomalous expansion of water. Why? Because every other substance contracts on expanding, whereas the water expands on cooling. Sorry, other substances will contract on cooling, whereas the water will expand on cooling. I repeat, when we withdraw heat from a substance, that is on cooling, other substances contract, whereas water expands, and this is known as anomalous expansion of water, right? So if I draw a curve which represents the density, uh, yes. Here we draw the density, let's say density of water, and if here we draw the temperature, right? So when we start cooling water, the density will drop, right? No, sorry, it's the volume, sorry, the volume will drop, volume of water, the volume will drop, and as soon as the temperature reaches to 4 degrees centigrade, it start expanding, right? This is how the volume of the water is changing. That is, as soon we are cooling, let's say we are the water is at graph, let me show it like this. We are cooling, cooling it. This is your y-axis, this is your x-axis, right? Here it is the volume, here it is the temperature. Temperature starts from 0, then let us mark as 4, and then let's mark it as, let's say, some 20, right? So if from here the water's volume is decreasing, 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 and then it increases, 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 right? So at this point it has its minimum volume, that is at 4 degrees centigrade it has minimum volume. On the other hand, if we draw the density curve for density, the same graph, if I draw the curve for density of water, here the density will increase, 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 and then start dropping. At this 4 degrees centigrade, water will have its maximum density. This is rho max. this will be your rho max, and this will be V minimum. For this minimum volume, it will have its maximum density. Why? Because density is equals to mass upon volume, that is density is inversely proportional to volume, right? Density is inversely proportional to volume. So when we cool water, that is whenever the heat is been withdrawn from water, it will cool, it will contract up to 4 degrees centigrade. But if we further cool it below 4 degrees centigrade, it will start expanding. That means at 4 degrees centigrade, it has its minimum volume and maximum density. So after 4 degrees centigrade, if we further cool water, it will start expanding, and again its density will start decreasing. So at 4 degrees centigrade, water has its maximum density and minimum volume, and this behavior of water of expanding when heat is being drawn from water below 4 degrees centigrade is known as anomalous expansion of water, right? This is known as anomalous expansion of water. Now let's next come to the next topic, is your calorimetry. Before studying calorimetry, I would like to introduce a term which is going to be used here repeatedly, and that is your specific heat capacity, right? Specific heat capacity. What is specific heat capacity? It is the amount of the heat required to change the temperature of unit mass of a substance by 1 degree centigrade, right? It is the amount of the heat required, the temperature required. It is the amount of the heat required to change the temperature of a unit mass of substance by 1 degree centigrade, right? So, and it is represented by small c, right? Its SI unit is joule per kg Kelvin, right? Joules per kg Kelvin. So what is specific heat capacity? Sorry, specific heat capacity is the amount of the heat required for a unit mass of a substance by 1 degree centigrade. So a change in the temperature by 1 degree centigrade is equals to the change in Kelvin. Suppose the temperature changes by 1 degree centigrade, then in Kelvin scale also it will be changing by 1 degree only, right? So specific heat capacity, again I am repeating, it is the amount of the heat required to raise the temperature of a unit mass of a substance by 1 degree centigrade. It is denoted by small c, and its SI unit is SI unit is your joule per kg Kelvin. This is the SI unit of specific heat capacity, right? Now, if heat is being supplied to a body, suppose the heat is being represented by capital Q, right? Capital Q, we will be representing heat with capital Q. Now, if this heat is being supplied to a body, then there will be a change in temperature, right? This is what I told. When we supply heat to the body, the temperature of the body will increase. That is there will be a change in temperature, right? So when you supply heat, the change in temperature delta T is directly proportional to the amount of the heat supplied. The change in temperature is directly proportional to the amount of the heat supplied. That is, for a given mass of a substance, if you are supplying a certain amount of the heat, its temperature will change by a certain amount. If you increase the amount of the heat, the change in temperature will also increase. That is a direct. There is a direct relation. More heat is being supplied, more temperature will be changed. Now, for the same change in temperature, if mass is increased, you will have to supply the more heat. You will have to supply more heat to that substance, right? So the amount of the heat required to change the temperature of a mass of a substance for the same change in temperature, if we increase the amount of the mass of the substance, the amount of the heat required will also increase, right? I will give you the examples and everything will be clear from there. So combining this, what we'll get, that Q is directly proportional to delta T and M. Now, to remove this proportionality and convert this inequality, we will have to multiply with a constant, and that proportionality constant over here is the specific heat capacity. So this equation becomes as Q is equals to C into delta T into M, right? So what I want you to understand is that whenever heat is being supplied to a body, the amount of the heat supplied is directly proportional to the amount of the change in the temperature you are supposed to bring. And this amount of the heat supplied is also directly proportional to the mass. More is the mass, more will be the heat required. Here M is kept constant, whereas here delta T is kept constant. Now let's understand with an example. Let's suppose in a container I have, let's say, 1 kg of a substance, 1 kg of a substance, and another another container also I have the same mass of a substance, that is 1 kg of a substance. But with the when I heat both the substances with the same burner, why same burner? Because I want to assure that the rate of the heat supplied to the bodies is same. Then if I want to change the temperature from, let's say, from 0 to 5 degrees centigrade, and here I want to change the temperature from 0 to, let's say, 15 degree centigrade. Now if heat is being supplied with the same burner, then the amount of the or the time in heating this, the time in changing the temperature from 0 to 5 degrees centigrade will be less as compared to the time required to heat the same mass of the body from 0 to 15 degree centigrade, right? That is, if we increase the range of change in temperature, the amount of the heat supplied will increase. Why? Because if more time is required, it means we are supplying more amount of heat here. Therefore, if the range of temperature increases, that is the temperature to which we have to change the temperature, the range up to which we have to change the temperature, if that increases, the amount of the heat required will also increase. Now suppose I have two containers, right? One container is having a mass of 1 kg of a substance, and another container has 5 kg of substance. For both the containers, the temperature is to be changed from 0 degree centigrade to 5 degree centigrade, and here also 0 degree centigrade to 5 degree centigrade, right? So what is the change in temperature to be brought over here? Delta T is equals to 5, and here also delta T is equals to 5. So delta T is kept constant, but in one container the mass is 1 kilogram, and in the another container the mass is 5 kilograms. So if we supply heat to both the substances with the same burner, the time required to change the temperature of the bodies by the same range will be less for 1 kg of body and will be more for 5 kg body. That is Q, that is the heat will be heat supplied to 1 kg will be less than heat supplied to 5 kg. Why? Because the time required is more. Now suppose this burner is supplying 1 joule per seconds, right? If suppose the burner supplies 1 joule per second, and this burner is also the same burner, so it will also supply 1 joules per second, 1 joule per second. So if we require, let's say, 10 seconds here, we would require some time which is greater than 10 seconds. The time required here will be greater than 10 seconds, right? And because time required here is greater, therefore the heat supplied to this body will be greater. Therefore I write that Q1 will be less than Q5, that is heat required to raise the temperature of 1 kilogram of body by 5 degrees centigrade will be less as compared to the amount of heat required to raise the temperature of 5 kg of the same substance by the same range, that is 5 degree centigrade, right? So what ultimately we have concluded from here is that is the amount of the heat supplied to a body is directly proportional to the amount of change in temperature to be brought, and amount of the heat supplied to the body is directly proportional to the mass. More is the mass, more will be the heat supplied. So combining this, we'll get Q is proportional to M delta T. To remove the proportionality, we multiply with proportionality constant, so it becomes Q is equals to MC delta T. Here C is the proportionality constant, is known as specific heat capacity. Specific heat capacity. This specific heat capacity is the material property, that is, it is fixed for a given substance. Suppose copper has, if suppose copper has, let's say, X joule per kg Kelvin, and aluminium has, let's say, Y joule per kg Kelvin, and let's say water has Z joules per kg Kelvin, then these quantities are fixed, right? These quantities are fixed. That is, this specific heat capacity is the material property. It is fixed for the substances. It's not going to change. Therefore, this constant quantity is being used as a proportionality constant over here. So from here what we get an expression for the amount of the heat supplied, that is Q is equals to mc delta T, or in some books or in some places you may find Q is equals to mc delta theta, where delta theta means the same thing, change in the temperature, right? That is the final temperature T final minus T initial. This quantity is being taken as delta T, right? So and this is what is the expression for amount of the heat supplied to a body. Now, what calorimetry means is, see, we cannot measure the amount of the heat contained in a body. We can never measure the amount of the heat contained in a body. It is the only that how much heat is being transferred. This is the thing which could be calculated. Transferred means what is the amount of the heat withdrawn from the body, or what is the amount of the heat supplied to the body. Only this could be calculated, but you can never calculate what is the amount of the heat stored inside the body, right? The amount of the heat stored inside the body. So to study or to measure the amount of the heat transferred from one body to another, we use calorimetry. So what is the basic concept behind calorimetry? Calorimetry says that whenever two bodies at different temperature are brought in thermal contact, means that they are brought in contact in such a way that the heat energy can flow from one body to another, and the two bodies are at different temperatures, irrespective of their mass, irrespective of their specific heat capacity, irrespective of anything. It's only the temperature. That is, if the two bodies at different temperature are brought in contact with each other, the heat will always flow from a body at higher temperature to body at a lower temperature. I repeat that it is irrespective of mass of the body, it is irrespective of the amount of heat contained in the body, it is irrespective of the size of the body, it is irrespective of the state of the body, it is irrespective of anything. That is, whenever two bodies of different temperature are brought in contact with each other, the heat will always flow from a body at higher temperature to body at a lower temperature, right? And assuming that there is no loss of heat in the surrounding, there is only exchange of heat within these two bodies, then the amount of the heat lost by the body at a higher temperature is equals to amount of heat gained by the body at lower temperature. I repeat, the amount of the heat lost by the body at higher temperature is equal to the amount of the heat gained by the body at lower temperature. Body amount of the heat lost by the body at higher temperature is equal to the amount of the heat gained by the body at lower temperature, and this is known as principle of calorimetry. That is, your heat lost is equals to your heat gained, right? Heat lost is equals to heat gained. Whenever two bodies at different temperature are brought in contact with each other, the amount of the heat lost by the hot body is equal to the amount of the heat gained by the cold body. This is known as the principle of calorimetry, right? Now, how heat is being supplied, or let's not how, there are two things which happens when we supply heat to a body, right? One thing is, when heat is being supplied to a body or being withdrawn to a body, its temperature changes, right? Or or its state changes, right? When temperature changes, the specific heat capacity comes in picture, and when the state changes, the latent heat comes in picture. What is latent heat? Latent heat is the amount of the heat required to change the state of unit mass of a substance. Change the state of unit mass of a substance. So, and the SI unit for latent heat is joule per kg, right? Joule per kg. Why the temperature is not over here? Because Note the statement which I say, that whenever there is a change in temperature, whenever there is a change in temperature, there will be no change in state, and whenever there is a change in state, there will be no change in temperature. That is, suppose we are supplying heat to a solid substance, right? You are supplying heat to a solid substance. That substance will take that heat, will expand, and at a certain level, a time will come at which it will stop expanding, or sorry, it will continue expanding, but the change in temperature of that body will not be reflected. There will be no change in the temperature of the body, and this is the point when this body will start changing from solid to liquid. That is, the state of the substance will be changing. So what is happening is that when you are supplying heat to the body, initially when it's got expanding or the temperature was increasing, the kinetic energy of the particles of which the material has been made or the substance has been made was increasing, and this increase in the kinetic energy was reflected in terms of, in form of, or in form of temperature, right? It was being reflected in form of temperature, in which you can be easily measure using the thermometer. But if you further continue to supply heat, what will happen at a point? What happens? The amount of the heat supplied to the body is not helping the helping in increasing the kinetic energy of the particles. Rather, it increases the potential energy of the particles, because of which they change their orientation, and as the orientation changes, the state changes. And because the whatever heat is being supplied to the body is no more increasing the kinetic energy, therefore this heat is not being reflected in form of change in temperature. Rather, this heat is being used in changing the state of the body. And because this heat supplied cannot be seen in the form of temperature, therefore this heat is known as latent heat, where this word latent means hidden, right? Latent means hidden, because this heat is hidden, it cannot be shown in the form of temperature. This entire heat is being taken by the body to change the state of the substance, and this heat is known as latent heat. And it is defined as the latent heat, or the specific latent heat of a substance is the amount of the heat required to change the temperature, so change the state of unit mass of a substance, right? I repeat, specific latent heat of a substance is defined as it's the amount of the heat required to change the state of unit mass of a substance, right? Now, what are the change in the state? Change in the state are from solid to liquid, and from liquid to gas, or from gas to liquid, and from liquid to solid. Solid to liquid is known as melting. Liquid to gas is known as vaporization, right? Or solid to liquid is also known as fusion, and liquid to gas is known as vaporization, right? Now, gas to liquid is known as condensation, and liquid to solid is known as solidification. So this latent heat can be named as specific heat of fusion, specific latent heat of melting, latent heat of vaporization, latent heat of your condensation, latent heat of your solidification. So it's simply the name. Now, if the solid is being converted into liquid, and suppose 1 kilogram, or the unit mass of the substance has been taken, and x joule of energy is required, right? Then what will happen? This x joule of energy will be known as latent heat of fusion for that substance, latent heat of fusion, or latent heat of melting, or latent heat of freezing, because whatever the amount of energy will be given to the substance so that it changes from the solid to liquid, the same of amount of energy, if withdrawn from the liquid, it will convert into solid. What I mean to say is that suppose you have 1 kilogram of a substance, and you supply x joule of energy to that substance, and it changes to from solid to liquid. In the same manner, if you draw x joule of energy from the liquid, it will convert into solid, right? So whatever is the amount of whatever is the latent heat of fusion, same is the latent heat of solidification, right? Similarly, whatever is the latent heat of vaporization, same is the latent heat of your condensation. Only the difference is that in one case heat is being supplied, and only in another case the heat is being withdrawn, right? That is, from when the body is converting from solid to liquid, heat is being supplied. and when it is converting from liquid to solid, heat is being withdrawn, right? So latent heat is the amount of the heat required to change the state of the given substance. The name of the latent heat depends on from which state to which state you are going. That is, either you are going from solid to liquid, or from liquid to gas, or from gas to liquid, or liquid to solid, right? So from solid to liquid is known as melting or fusion. From liquid to gas is known as vaporization. From gas to liquid is known as condensation, and from liquid to solid is known as freezing or solidification, right? So latent heat comes in picture when the state is changing. So what we were talking is that whenever there is a change in temperature, there is no change in state, and whenever there is change in state, there is no change in temperature. So when heat is being supplied, two things can happen: either the temperature will change or the state will change, right? So suppose two bodies at different temperature are mixed with each other. What will happen? One body will lose temperature, another body will gain temperature. And in this losing and gaining, the state of the body can also change. Now, let me take an example over here. Suppose I have ice at minus 10 degree centigrade, right? I have ice at minus 10 degree centigrade, and I'm supplying heat to it. So let me represent it with the help of a diagram. What will happen? See, this y-axis is showing you temperature, right? And the x-axis is showing you the amount of the heat supplied. Now, let's say the ice is at minus 10 degrees centigrade. So when I supply heat, what will happen? The temperature of ice will change from minus 10 to 0 degrees centigrade, right? And the amount of heat supplied over here will be Q1, and this Q1 will be equals to MC delta T, where here C will be the specific heat capacity of ice, right? Rated as Ci, right? Specific heat capacity of ice. And what will be the delta T? Delta T will be equals to 10, right? Because we are moving from minus 10 to 0. Delta T will be equals to 10. And if you see carefully, what here is, this is a slant line, right? Q is equals to MC delta T, because there is a change in temperature. We are moving from minus 10 to 0, right? Now, when the ice is at 0 degree centigrade, if we further supply heat, what will happen? Heat is being supplied, right? This is heat. Heat is being supplied. There will be no change in temperature, but heat is being supplied. Now, heat is being supplied to this extent. So here we had ice at 0 degree centigrade. Now at this point we have water at 0 degree centigrade. Now if further heat is being supplied, what will happen? The water will change its temperature and it will rise to, let's say, it will rise up to 100 degree centigrade. And at 100 degree centigrade, what will happen? It will start boiling and changing its state from liquid to gas. So at this point, there will be no change in temperature, but still the heat is being supplied. So a graph will be drawn like this. At this point, there is water at 100 degree centigrade, and here we have steam at 100 degree centigrade. Now, if further heat has been supplied, the temperature of the heat will change, temperature of the steam will change, and it will rise. Now, here we had, at this point, the heat supplied is Q1. At this point, we'll have heat supplied is equals to Q2. At this point, we'll say that heat supplied, amount of heat supplied will be Q3. And at this, let's say it be Q4, right? So Q1 will be equals to M, specific heat capacity of ice, into delta T. Q2 will be equals to M into L, that is specific latent heat of fusion. Then Q3 will be equals to M C delta T, specific heat capacity of water, right? Then again Q4 is the amount of heat which is required to change the water at 100 degree centigrade to steam at 100 degree centigrade. So it will be Q4 will be equals to M into L, right? That is, this was latent heat of fusion. This will be equals to latent heat of vaporization, right? So the total amount of heat supplied up to this point will be equal to sum of all the heats, that is Q1 plus Q2 plus Q3 plus Q4, and this is equals to Q. So this is the total amount of heat required to change 100 minus 10 degree centigrade ice to 100 degree centigrade steam, right? So this is how the heat is being calculated for change in temperature and for change in state. Now, if two bodies are mixed together, suppose I have a container containing ice in it, right? And I put a metal ball which is at, let's say, 50 degrees centigrade. The ice is at 0 degree centigrade. So what will happen? This ice will take heat from the hot metal ball and will start melting, right? So let's say m mass of ice melts, taking latent heat as L, plus when the entire ice will melt, the water which is at 0 degree centigrade will start increasing its temperature. So the mass of water into specific heat capacity of water into delta T, right? Delta T. This will be the amount of the heat gained by the ice and water, and this same amount of heat will be lost by this metal sphere or metal ball. So let me write it as m dash. M dash is the mass of the metal sphere into specific heat capacity m dash of the material of which the sphere has been made, and delta T dash, that is whatever the change in the temperature of the sphere. So this is the amount of the heat lost by the sphere. The amount of the heat gained by the ice is equals to amount of the heat lost by the sphere. Delta T for ice, delta T here on this for ice and water, it will be equals to 0 minus T final, or T final minus 0. You can, we are simply taking the magnitude, and from here, because the initial temperature was 50 degree, and the heat will be supplied or exchanged between the two bodies until both reach to the same temperature, that is T final, right? So its temperature will change from 50 to T final. So the change in temperature here will be 50 minus T final. So delta T dash will equals to 50 minus T final, right? So this is how you will be we will be writing what writing your expression for amount of the heat loss is equals to heat gained, right? So this is how you will be using the principle of calorimetry for finding amount of the heat transferred from one body to another, right? So what you are supposed to do here is just simply find which body is losing energy and which body is gaining energy, or which body is losing heat and which body is gaining heat. So amount of the heat lost will be equal to amount of the heat gain. Now in losing heat or in gaining heat, if the state is changing, you take that heat energy as ml, and if its temperature is changing, take the heat energy as mc delta T, right? So the formula which we have studied till now is Q is equals to mc delta T. This is for the case when the temperature is changing, and Q is equals to m into L. This is for the case when the state is changing, and heat loss is equals to heat gain. This is the principle of calorimetry, right? So this is what is this is all about the calorimetry. Now next thing which we are supposed to study is your thermal conductivity, right? Thermal conductivity. Now suppose we have a solid substance. Let's say there is a cube, right? Let's say there is a cube. There is a cube, right? And we are supplying heat to the cube from this side. And the temperature of this is, let's say, T naught, and temperature of this is, let's say, T1, right? So when we are supplying heat, the heat will gradually pass from this phase to this phase, right? From this phase to this phase. So this heat which is being supplied from one phase to another phase will be directly proportional to the area of cross section and uh, area of cross section, and this heat will be directly proportional to the difference in temperature, that is T1 minus T naught, and this Q will be inversely proportional to time, right? Sorry, inversely proportional to the distance between this x, distance between the faces, right? Distance between the faces, inversely proportional to the difference distance between the faces, and this q will be directly proportional to the time. Directly, more is the time, more will be the heat supplied. Combining this, what we get q is equals to a into T1 minus T naught into T upon x, right? Proportional to, right? Proportional to. Then to remove this proportionality, we will write it as your q is equals to k into a into T1 minus T naught into T upon x, right? Upon x, right? Where here the k is known as the coefficient of thermal conductivity, right? K is known as coefficient of thermal conductivity. So the proportionality constant over here is K, and this is known as coefficient of thermal conductivity, and this is again a material property. For different materials it will have different values, right? So what expression do we have over here is that whenever we are heating a substance or solid from solid in such a way that it is conducting heat, that is a solid or a conductor which is conducting heat, then we will be heating it from one phase, right? Suppose this is the solid, we are heating from this side, so this end will have temperature T naught and this end will have temperature T1. This distance is x, and the phase from where we are heating is having an area cross section of A. Then the amount of the heat supplied is given as A into T1 minus T naught into T, that is the amount of time for which the heat is being supplied, upon x, and into K is known as the coefficient of thermal conductivity. Now, if I take this stay from P from here to this denominator, what will happen? We will write it as Q upon P is equals to Ka T1 minus T naught upon x. So this is known as rate of flow of heat. We write it as H is equals to dq by dt, dq by dt, and this dq by dt is equals to k a dt by dx, dt by dx. Now, if you see, when we move from your this end to this end, that is, if we move in the direction of x, T1 is less than T naught. Why? Because we are supplying heat to this end, and heat is being gradually transferred from particle to particle, and it reaches to this end. Therefore, the temperature T1 will always be less than temperature T2. Therefore, because of this, there will be a minus sign over here. That is the rate of flow of heat. Rate of flow of heat is given as H is equals to dq by dt, which is equals to minus k a dt by dx, right? Dt by dx. This is the rate of flow of heat. So this is the rate of flow of heat. Now, if suppose we are heating a body, what will happen if you are supplying heat continuously? After a certain interval of time, what will find that from after if you check at different points in this conductor, the rate of flow of heat, the rate of flow of heat at every point becomes the same. Although the temperature at every point is not same, it would not happen ever, but the rate of flow of heat from every point is same, and that point is known as steady state. What it is known as? Steady state. What is steady state? Steady state is the state when the rate of flow of charge from every point of the conductor becomes equal, and that point is known as your steady state, right? Steady state. Now next what we are supposed to do is your mode of heat transfer. So modes of heat transfer. There are three modes, that is your by conduction, second is by convection, and third is by radiation, right? For these three mode of heat transfer and further more in this chapter, we will discuss in our next video, right? Along with this, I would like to inform you about the sale which is going on from, that is from 14th of August to 16th of August, for your subscription for our MemoNeet app, right? For this MemoNeet app, you can just, there is a very a huge discount being given to the students who will buy the app in between these days, right? So just go and look into the YouTube. For more details, you can look into the description of this video, right? So this is all from my side from this for this video. Thank you.